Today we'll talk about approximation algorithms. So what are approximation algorithms? Why do you need approximation algorithms? So there are some problems which people don't know how to solve. For example, there are some NP hard problems. For NP hard problems, we don't know any polynomial time solution. So what do scientists do when we don't know how to solve problems? They just find another problem and solve this problem instead. So what we do for some NP hard problems? Let's say there is some hard problem, and in this problem you need to minimize something. So you want to minimize some function. You want to find shortest path or some minimal packing of something. So there is some problem which wants to minimize something, and there is some optimal solution. So let's call it optimal solution. We don't know how to find optimal solution in polynomial time, but we can find some another solution. Let's say S. It's our solution. And our solution will call it alpha optimal if our solution, let's say, is at least alpha opt. So if we can find some solution which is at most alpha greater than the optimal solution, we'll call this algorithm alpha optimal solution, alpha optimal algorithm. Yeah. Well, for example, what can happen? So if you want to find the shortest path, so shortest path is polynomial solvable, but in some strange models they may be hard to find optimal path. So you want to find the shortest path. And for example, if you can find the shortest path, which is alpha, let's say 1.1. So if alpha is 1.01, it means you can find shortest path, but you can find some path, and this path you found is just 1% longer than the optimal path. No, it's working, but no idea. Some Wi-Fi problems maybe. So this is pretty good, right? So you can find some solution which is at most 1% worse than the optimal solution. So that's pretty good. In some other cases, you may find something like alpha equals to like 2. What does it mean? So you find some solution and it is twice worse than the optimal solution. Is it good or bad? It depends. So if you want to find the shortest path, and your program says that this is some path, and I know this path is like twice longer than the optimal path. Not very good, but not terrible. So it gives you some information about the optimal path. So you find some path, and you know that the optimal path is at most twice shorter than the path you found. It's some information, so yeah, it's not great, but not terrible. Okay. In some cases, situation is even worse. So in some cases, there are algorithms with when alpha is not a constant but some function. So for some algorithms, alpha, let's say something like log n. So the bigger your problem is, the worse your solution becomes. So if for some small problems you have pretty good approximation, for some big problems you have worse approximation. Also happens. So it all depends on what problem you actually solve. So for different problems, so it's not like there's no like unified method for solving NP hard problems. For each NP hard problem, not only NP hard, for any hard problem, there may be different approximation algorithms, and we will talk about different ways how to build approximation algorithms today. Well, so let's start with something simple. Let's solve vertex cover problem. So what's happening in vertex cover problem? In vertex cover problem, you have some graph. Let's build some graph. Something like that. let's see, something like that. So you have some graph, and you want to find the minimal number of nodes, such that if you take these nodes, you cover all the edges of your graph. So you mark some nodes, for example, this node, and this node. So every edge of your graph has at least one of the ends in this set. Yeah? So it's minimal possible set of nodes, such that for each edge, at least one of its end is covered by this set. It's called minimal vertex cover problem. Minimal vertex cover problem is NP hard problem. So we don't know how to solve this problem. You could solve this problem for bipartite graph, and we discussed it when we talked about maximal matchings. So if you have a bipartite graph, it's actually possible to solve this problem in polynomial time using just maximal matching problems. It's actually dual to the maximal matching problem, like we discussed in linear programming. But for non-bipartite graph, it's NP hard problem. We don't know how to solve it. So let's try to build some approximate algorithm. So how to build approximate algorithm for the vertex cover problem? Very easy. So let's do it like this. I'll just erase this. Let's take any edge of the graph. For example, this edge. So this is a nice edge. Yeah? We need to cover this edge. So at least one of these ends must be in the vertex cover. What can we do? We can take both ends of this edge to our set. So let's mark both ends of this edge. Nice. Now let's take any edge which is not covered by our vertex cover. For example, let's take this edge. For this edge, again, at least one of its end must be in the vertex cover. So let's take both ends of this edge to our vertex cover. So take this end and this end. That's all. Now all edges are covered, so we have some vertex cover. Let's prove that we have two optimal solutions. So again, we find some vertex cover, and there is some optimal vertex cover. I want to prove that my answer is at, more than 2 times optimal. So I take at most twice of the number of the nodes in the optimal answer. No, why is it true? No, it's quite obvious actually. What did we do again? We take some edge. So every time we take some edge which is not covered, and take both these ends to our vertex cover. And then again, we take some edge which is not covered and cover both its edges, both its ends, and so on. So every time you take some edge which is not covered by your current set and take both its ends to your vertex cover. Now let's see. If we take k edges here, then we take, so if we have k edges, then the answer is k. Then our answer is 2k, right? What about optimal answer? In the optimal answer, we need to cover all these edges, but these edges do not share any ends. So to cover these k edges, we need at least k vertices in our vertex cover. So for each of these edge, at least one of its ends must be in optimal vertex cover. So at least one of these ends is, so this red is optimal vertex cover. So in the optimal vertex cover, there must be at least k edges, k nodes. So the optimal answer is at least k, and our answer is 2k. So it means that our answer is at most twice worse than the optimal answer. That's all. That's how we build the two optimal algorithm for the vertex cover problem. Okay, this was quite simple algorithm. So sometimes you have very simple algorithm which gives you some approximation of your optimal solution. Sometimes it's a little bit worse. For example, let's solve the weighted vertex cover problem. So in the weighted vertex cover problem, you have some graph, but each node has a weight. And you want to minimize not the number of nodes in your vertex cover, but the total weight of your nodes. So each node has some weight. And we want to minimize the sum of weights of your nodes from your vertex cover. Is there a better approximation for vertex cover problem? I'm not sure about it. It's a good question. I don't know what's the best known approximation for vertex cover problem. No idea. Maybe there's some algorithm. No, I don't think randomization will help you. Okay, you can Google it. I'm not sure about what is the best known approximation for vertex cover problem. Never think about it. Okay. Good questions. Okay, so let's go next. Let's go to weighted vertex cover problem. So in the weighted vertex cover problem, you have again you have weights, and you want to minimize not the number of nodes in your vertex cover, but the total weight of your nodes in the vertex cover. What you can do in this case, you can do a very cool trick. You can use linear programming, like we discussed in the few lectures ago. Linear programming is polynomial solvable. So if you write a linear program, you can solve it in polynomial time. It's pretty hard, but it's possible. So what we can do? We can write a linear program for this problem. So what is linear program? No, we want, let's say, x v belongs to 0 or 1. And we want to, for each edge in our graph, we want at least one of its ends belong to this set. We want xu plus xv be at least 1. And we want to minimize the sum of xv multiplied by weight of this. Minimize. So that's the integer linear programming, right? So this thing, again, we have linear inequations here, and we have linear function to minimize. The problem is it is a linear integer program. Yeah. So linear integer programming is again NP hard, obviously. Yeah. But what you can do, you can here you can modify this these things. So you can think not about integer solutions, but about any solutions. So what if we say that x is not an integer variable, but it can be some real variable. So it belongs to set from 0 to 1. Then this is a real number integer problem. Yeah, so in the linear program. So linear program for real variables is solvable in polynomial time. So we can solve this linear program in polynomial time using some. Again, we didn't discuss any polynomial algorithms for linear programming, but there are some polynomial time algorithms to solve the linear programming problems. What next? What next? You can use simplex method as not polynomial, maybe polynomial, but no. So simplex algorithm is not exactly a polynomial time algorithm. Again, you can use it in practice. It usually works pretty good, but it's not exactly polynomial time algorithm. No, we discussed it last time. So there are some polynomial algorithms which are not usable in practice, but they are still polynomial. And there is a simplex method, which is not polynomial, but pretty fast in practice. So you can use simplex method to solve this problem in practice. Now, what next? You solve this linear program and you have some real numbers here. But you want not real numbers, you want integer numbers. So what you can do, how you can get from these real numbers to some integer solution? You can round these real numbers. So let's round these real numbers to the integer numbers. So let's say that x prime v is equal to 1 if xv is at least 0.5, and it is 0 if xv is less than 0.5. So if we look at these integer numbers, then all these inequations will be satisfied. Yeah. So for each inequation, if we have sum of two real numbers at least 1, then one of these numbers, so here is xu at least 0.5, or xv is at least 0.5. Yeah. So for each this inequation, we have at least one of these variables at least 0.5. So this thing will give you some feasible solution for this linear program. What about optimality? Let's see. So if we look at this variable x prime and this variable x, then we'll say that this new variable is no more than twice the xv. Yeah. It means that in this function we'll have at least twice the optimal solution. It means the solution we have by solving this linear program and then rounding all the variables like this, we will have two optimal solutions for this problem. And that's actually quite universal method for solving for some approximation, for building some approximation algorithms. So for some problems it's actually useful. So you just take your problem, build a linear program for this problem, solve this linear program for real numbers, then round these real numbers to some integers, then you have some integer solution, and this integer solution will be quite close to the optimal solution. Good. So again, there is optimal solution. Yeah, optimal solution is a feasible solution for this system. So we find the optimal solution for the system. So optimal solution cannot be less than this. Yeah? So we find some solution. It is less or equal than the optimal solution. And then we find this integer solution, which is at least at most twice larger than this solution. That's all. So that's how you build that's how you build two optimal solutions for weighted vertical problem. Okay, let's have some more problems. Yeah. It happens because we only rounded up when we have at least 5. So the worst case is when x equals to 0.5, then we increase it twice. Yeah, that's the worst case. Cool. Let's go next. Next problem we'll discuss is the traveling salesman problem. So what about traveling salesman problem? We have some. Let's say we have a full graph. So we have a full graph of n nodes, and we have some costs of moving from one node to another node. So let's see. CUV is the cost of moving from U to V. Yeah, like this. And we want to visit all the nodes exactly once and minimize the total distance. So we want to build some permutation P1, P2, and so on, Pn, and minimize some C, Pi, Pi plus 1. Yeah. So this is classical traveling salesman problem. Yeah. So you have some cities and you want to visit all the cities exactly once and minimize the total distance you travel. Unfortunately, this problem is not, so this problem is obviously NP-complete, but what's worse, for this problem there's no any approximate algorithm. Let's prove it. So you cannot build approximate algorithm for this problem for any value of alpha. No, why is it true? Well, because any approximation of this problem is also NP-complete. Let's prove it. What you can do? Let's say you build some approximate algorithm for this problem. So you build some algorithm which finds the alpha optimal solution for this problem. What you can do? You can reduce the problem of finding combinatorial path in a graph to this problem. So let's say you have a graph. Yeah. So you have some graph. I wanted to have combinatorial path. Like this. Let's say you have some graph, and you want to find a combinatorial path in this graph. It is NP complete. So if we manage to find the combinatorial path, it means we solve this problem in polynomial time, right? So how to find the combinatorial path in a graph using approximation algorithm for this transcendence algorithm problem? It's quite easy. So you build the following graph. You build a graph. So you make the cost of the edge equal to 0 if there exists an edge. So for any edge, you set cost to 0. And for all other edges, you just make cost equal to 1. So you add all other edges with cost 1. So 1, 1, here 1, and so on. So you just make all absent edges with 1. Yeah. And so on, like this one, and so on. So you build a full graph. Each edge from your initial graph, you set cost equal to 0. For all other edges, which not exist in your initial graph, you set cost equal to 1. Now, if in this graph there is a combinatorial path, then the optimal solution is 0. Yeah. So there is combinatorial path. Then opt is 0. When opt is 0, then any approximate solution must return solution with value equal to 0, right? So if opt equal to 0, then your ends must be not greater than alpha opt. And since opt is 0, it must be 0. So you build this graph, run your approximate algorithm, and if your approximate algorithm returns 0, then you find the combinatorial path. And if your approximate algorithm returns non-zero, it means that optimal answer is not 0. And if optimal answer is not 0, it means your graph doesn't contain any combinatorial path. So we just solved the combinatorial path problem using our approximate algorithm of transcendence problem. It is NP complete, so it means our problem is also NP complete. So finding any approximate solution for the transcendence problem is NP complete problem. Ta-da! That's all. But what's good news? Sometimes we can find the approximate algorithm for this problem. And it's case when you have what's called metric transcendence problem. Let's say we have a transcendence problem, like this. But we have a triangle equation. So for any free nodes, we have C, let's say UV is not greater than CUW plus CWV. So we have some metric, basically. We have some, basically, well, that's how the metric space works, right? So you have you have these costs, and this cost satisfy this triangle equation. It's actually pretty common. So if you just think about it, so if you travel from U to V, it must be not greater than travel from U to W and then from W to V. For example, if you just want to visit all the nodes, and you want to visit each nodes not exactly once, but you want to visit all nodes at least once. Yeah. So if you want to visit each node at least once, then you can reduce your costs to the shortest path from U to V. So if this U to V is not a cost but the shortest path, then for shortest paths is actually you have triangle inequation, right? So again, if you have trial and Taylor's problem and you have triangle inequation, then we can build a two approximate solution. Let's build two approximate solution. Nice. So how to do it? Let's see. How to build approximate algorithms? You need to build something which kinda get you some information about optimal answer. So what's the problem here? We want to find some answer which is close to the optimal answer, but we have no idea about optimal answer. So we need to build something which gives us some bound of the optimal answer. In our case, we will build a minimal spanning tree. So let's build a minimal spanning tree in our graph. So we have some graph, we build some minimal spanning tree. We're using some Knapsack algorithm or Prim algorithm, yeah, Kruskal, yeah, Kruskal. Okay, so let's build a minimal spanning tree. I claim that the optimal solution cannot be less than the minimal spanning tree. Why is it true? Well, let's see. The optimal solution is a path which contains all the nodes of the graph. Yeah, the path is a tree. It's quite simple tree, but it is a tree. So the Hamiltonian path in a graph is some spanning tree of the graph. So if we build a minimal spanning tree, it will be less or equal than the optimal answer, right? Again, because if you take the Hamiltonian path is a tree, some spanning tree. Yeah. So we build a minimal spanning tree. Minimal spanning tree is less or equal than some spanning tree. So minimal spanning tree is less or equal than optimal. Now we have some bound on the optimal answer. We know that the optimal answer is at least the value of this minimal spanning tree. Yeah. Now, what we need to do? We need to build some answer which is at least twice the total length of this minimal spanning tree. Can you see how to do it? So I built this minimal spanning tree. I know that the optimal answer is greater or equal than my spanning tree. Now, what I will do, I will build my answer, which will be no more than twice minimal spanning tree. If I manage to do it, then my answer will be at most twice minimal spanning tree. It will be at least twice an optimal answer. So I will build two optimal solutions. Yes, and the way you do it, you just make a traverse of this tree, basically. So again, why MST is less than opt? Because again, what is the optimal answer? Optimal answer is some Hamiltonian path. Yeah. So there is some optimal answer. So optimal answer is a path. Path is a tree. So optimal path is some Hamiltonian path, or some spanning tree. We build a minimal spanning tree. Minimal spanning tree is less or equal than some spanning tree. So optimal answer is a path. Path is some spanning tree. So the total length of the edges in the minimal spanning tree is less or equal than the total length of your Hamiltonian path. Just because, again, Hamiltonian path is a path which walks through all the nodes of your graph. So you visit all the nodes of your graph, so you have some spanning path, basically, yeah? So the path is a tree. So, so how to build your answer at least twice, at most twice the size of this minimal spanning tree? You start from some node and just make traverse of your tree. So you start here. Basically, you make DFS of your tree, right? So like this. Like this. So total length of this path will be twice the size of MST. And now again we visit each node at least once, and we want to visit each nodes exactly once. So to visit each node exactly once, we will just shorten this path by eliminating any duplicates. So we start from here again. We visit these nodes. Now here I already visit this node, so I will just go from here straight to here. Now I visit this node, I will go straight to here. I visit this, so I'll go straight to here and then straight to here. Now, this path will be my answer, so this is answer. And since I have this triangle inequality, total length of this path will be at most twice the size of the minimal spanning tree. So again, my path is at least twice the size of the minimal spanning tree. Minimal spanning tree is at less or equal than the optimal solution. So my solution is no more than twice the optimal solution. Ta-da! That's all. That's all. That's how you build the two optimal solution for the traveling salesman problem in this matrix. But we can do even better. We can do even better. For traveling salesman problem, we can build 1.5 optimal solution. So how to build better solution? Let's do it like this. We can say, well, yes, we need to, yes. If you want to build a not cycle but path, you just remove one edge. Yeah, right. I build a cycle. If you want to build a path, you just remove one edge. Yeah. Now, we can do even better. So let's start by building the. Let's do something like that. Like this. So this is your mistake. Again, I want to build my answer, which is not again, why I have two here? I have two here because what I did before. I doubled all the edges and then built the Euler cycle. Yeah? So what we did here, we doubled all the edges of the graph like this, yeah, and then build the Euler cycle of this graph. But we can build Euler cycle without doubling all the edges. So, what I want to do, I want to build a Euler cycle of this tree, yeah, but without doubling all the edges. How to build the Euler cycle? To build the Euler cycle, you need all the degrees of all the nodes of your graph be even. Yeah. So what's the problem here? Why can I build the Euler cycle without doubling all the edges? Because I have some odd nodes in the graph. So let's mark all nodes of the graph. So I have these nodes of degree 1, this node of degree 1, this node of degree 1. Here degree is 4, it's even node, it's fine. Here I have even node. Here I have some odd node. And these nodes are odd nodes. Yeah. So I have like 1, 2, 3, 4, 6. I have 8 odd nodes in my graph. Now, what can I do next? I want all these nodes to have even degree. So right now, all these nodes have odd degree, and I want to have even degree. What I can do, I can connect these nodes. So I can make pairs of these nodes and connect them in pairs, so that the degree of all these nodes will be even. So again, I make something like that. I connect, let's say, these nodes, and for example, these nodes and these nodes, something like that. So if I take the tree plus these nodes, I will have some Euler graph. So now degrees of all nodes are even. So in this graph, I can build Euler cycle. This Euler cycle will connect all the nodes of this graph. So now, the length of my path will be equal to length of MST plus the total weight of these new edges. These new edges is some matching. Yeah. So we actually take some minimal spanning tree plus some matching here. So let's find the minimal possible matching. We didn't discuss this algorithm in this course, but it's possible to find the matching of minimal weight even if the graph is non-bipartite. We talked about congruent method for bipartite graphs, but it also can be extended to non-bipartite graphs. So for non-bipartite graphs, you also can find the minimal possible matching. So what is the, so now our answer is no more than length of MST plus the weight of this matching. Yeah. No, we already know that length of MST is at least opt. So what about the length of this matching? I claim that the length of my matching is no more than half of the weight of the optimal answer. Now, why is this true? Well, because let's look at the optimal answer. So optimal answer is that we had cycle. Let's talk about cycle. It's true for paths also, I believe. I believe it's also true for cycles. Let's talk about cycles. It will be easier. So let's have some optimal answer. Yes, if you want to find the optimal path, it's a little bit different, but it's still the same. So this is the optimal answer. So optimal answer is some combinatorial cycle which goes through all the nodes of your graph. So in this optimal cycle, there are these 8 nodes somewhere. So somewhere on this cycle, there are these 8 nodes. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So these 8 odd nodes are somewhere in this cycle. So what I want to do, I want to build the matching which has a weight at most half of the size of the optimal path. Again, this opt is the length of this cycle. I want to find a matching which has weight half of this cycle. Can you spot this matching in this picture? What we want to do? We want to build a matching, yeah? So how to build a matching from a cycle? So yes, we can just match the adjacent nodes, yeah. So let's take this, this, and this. So it looks like half of this cycle, right? It actually may be, but since we have weight graph, the size of this matching may be more than half of this graph. But if we look at another matching like this, so let's take another matching like this. Now, the sum of these two matchings is opt. So one of these matchings has weight half of the opt. So again, we have two matchings. So we have M1 plus M2 greater than opt. Is we take minimum of this, minimum of M1 and M2. It will be not greater than half of this opt. And since here we find the minimal possible matching, it will be no more than half of the optimal solution. So now we have the answer will be no more than optimal solution plus half of the optimal solution. So our answer will be no more than 3 to optimal solution. That's all. So that's how you build 1.5 approximation of the traveling salesman problem. And for the long time it was the best. So for this problem I actually know the story. So for this problem is actually for a long time it was the best known approximation for this problem. About a year ago, I think, yeah, something like that, somebody found the better approximation for this problem. So the best known approximation for the traveling salesman problem is like 3 over 2 minus epsilon. And this epsilon is really small epsilon. So So there is some algorithm which is polynomial and which give you a slightly better approximation, but this epsilon is really adjusted. So it's good in theoretical sense. So in theory, there is some algorithm which is slightly better, but in practice, this is like the best known algorithm for this problem. Yeah, exactly about, yeah. I'm talking exactly about this thing. So how long ago was it? Yeah. There's no date here. 2020, yeah. Okay, 2 years ago. Only 1.5 years ago. It was in October. They came even better approximation. Oh, I didn't know about it. Okay, I need to investigate. So they found even better approximations. Cool. Next. Let's move to the knapsack problem. For the knapsack problem, the situation is even better. Cool, I'll read it. Seven, 5 approximation photographic. Nice. Okay, I'll read it after. Oh no, 2012, yeah. Okay, I'll investigate. So, let's talk about knapsack problem. So, what is a classical knapsack problem? You have some items. Each item has weight and some value, some cost. Some price, something like that. So, we have the weight of the item. And we have some CI is the, let's call it the cost. It's not the cost, it's like the value of product. What we want to do is to put some items in a knapsack of the size S, so that the total weight of these elements is no more than S. So I want to find some subset of elements, so the total weight is no more than S, and the total value is maximized. It's classical knapsack problem. Knapsack problem isn't P-complete again. I believe we discussed it a year ago. So what can we do? Well, first of all, let's build some simple algorithms. So let's try some greedy approach. Let's build some really simple greedy algorithm to solve knapsack problem. So we will sort all the items by the, like, how it's called? I don't know how it's called. By the, like, what? That's fine. So let's sort the so all the items by the ratio of the cost divided by the weight. Sort by CI over W. And now let's put all the items in a knapsack in this order. Will it be some alpha optimal solution? What do you think? So again, I sort the items by this ratio and then add them one by one in the knapsack. If I can add the item in the knapsack, I just add it, and so on. Will it be too optimal or not? What do you think? Unfortunately not. This algorithm is not optimal for any alpha. Can you find the bad example for this problem, for this algorithm? What is the best test? What is the worst test case? So let's try to build. Let's say for example s equals to 1000. So I have a knapsack of size 1000, and let's have two items. So the total weight of these two items is greater than 1000. So I can put both these items in a knapsack. But in optimal solution, you need to put second element, and my solution will put the first element. Can you build this example? Yes, right. So let's have two items. First item has weight of 1 and a value of 2. And second item has weight 1000 and weight 1000. So the ratio here is 2, the ratio here is 1. So I sort them like that and try to put them in the knapsack in this order. So I put this item first, and this item I can't put since it will not fit in my knapsack. So I will put on. So my solution will put only this first item. So the answer will be 2, but the optimal answer is 1000. Yeah. So my solution is like 500 times worse than the optimal solution. And you can put any numbers here actually. So this solution is not alpha optimal for any value of alpha. But let's improve it. Let's do it. So how to improve this solution? Let's do it like that. Let's run this greedy algorithm and then take maximum of two things. Maximum of result of this greedy solution and the value of the maximal element. So Cmax. So let's find one item with maximal value and take maximum of result of this greedy solution and this maximal element. And I claim this solution is actually too optimal. So this solution is actually too optimal. Why is it true? Well, let's see. So let's solve the other problem. Let's solve the problem, knapsack problem, when you can split the element. So let's say you have not integer problem, but again you have some real number problem. So you can, for each element, you can split the element into parts and take some part of the element. And if you take some part of the element, you will have like again, if you take part of the element, you p, then the value, the weight will be pvi and the cost will be pci. So for each element, pi, let's say for each element we can take a part of this element. So the again weight of the value will be scaled proportional to this part. Yeah? How to solve this problem? So what is the optimal solution for the problem if you can take not the whole element but the part of the element? Well, for this problem it's easy to see that the greedy solution actually works. So if you can take not the whole elements but the parts of the element, then the greedy solution is the optimal solution. Again, because you take the elements, that's what you want to do. Yeah. So you want to sort the elements by this ratio and then take the elements in this order. Last element will be just, for the last element you take not the whole element but the part of the elements. So this is something like that. So this is your knapsack. So you take the first element, then the second element, the third element, and so on. So for the last element you take only this part of your element. Yeah. And this obviously will give you the optimal solution. No, again, because each time you just maximize the ratio of your current value over your over the weight you use. Yeah. again, if you look at like the on the function, if you look at the function of your current value, so it goes like this. So first you take the optimal element, then less optimal, less optimal, less optimal, and so on, something like that. And you just stop your function here. So yeah. So this is the sum of values, and this is the sum of weights. Yeah. So that's how your value grows when you put your elements. And you want this function to grow higher here, and so you sort element by this ratio. Now, what happens here? So here, so these elements actually, so this sum is actually my greedy solution. Yeah, and this last element is just one element. So the length of this element is greater or less local than C max. So my optimal solution is no more than greedy solution plus C max. And now again, if I take maximum of these two values, I will have at most half of this optimal solution. So maximum of greedy and C max will be at least half of the optimal solution. Yeah, you can think, yes, this is another way to think about it. Yeah. So if our greedy solution didn't find the half of the optimal solution, then this last element must be greater than the half of the optimal solution. That's another way to think about it. Yeah. Great. So we find some greedy solution, and this element didn't fit. So if this value is less than half of the optimal solution, then the weight of this element must be greater than the half of the optimal solution. Yeah. It's another way of saying the same thing actually. Nice. So that's two optimal solutions for the knapsack problem. Very easy. But for knapsack problem, situation is even better. What interesting about knapsack problem? For a knapsack problem, you can build alpha optimal solution for any value of alpha. So for any value of alpha, you can build approximate solution in polynomial time. Let's say so. For any epsilon, let's say, you can find answer which is at least, let's say, 1 minus epsilon opt in polynomial time. Again, for knapsack problem, for any epsilon, you can build 1 minus epsilon solution in polynomial time. That's interesting. I will first we'll discuss one algorithm. So there's two ways, just to show you the difference. First, let's discuss the algorithm. So sometimes for some problems, you have situation like that. So for any epsilon, you can build a polynomial time approximation for this epsilon. But it is polynomial for any epsilon, but the degree of your polynomial depends on this epsilon. So we'll talk about it right now. So if you pick some constant value of this epsilon, let's say epsilon equals to, let's say 0, 0, 1, like this. So I want to find a solution which is like 1% less than the optimal solution. Then for this value of epsilon, you will have some polynomial time solution. But the degree of this polynomial will depend on this epsilon. So if you take smaller value of epsilon, you will have slower solution. Yeah. Okay, I'll just show the algorithm just to see what I mean. Let's do it like that. Solution. Let's look at all the items. Let's split them into two groups. Group number 1, all the elements with costs less or equal than epsilon opt. Now let's see. What you can do if all your elements have value less than epsilon multiplied by opt. How can you get epsilon approximation for this problem? What do you think? Let's say if all my elements have value less than epsilon opt, how to find y minus epsilon optimal solution? It's exactly here, actually. Yeah, you just build the same greedy algorithm. But in our case, this last element will be less than epsilon opt. Yeah. So again, so I just make this the same greedy algorithm. So my opt will be, I just make the same formula. Greedy plus epsilon opt. It means my greedy solution is less 1 minus epsilon. So I just make the same greedy solution, and it will give you 1 minus epsilon approximation. Quite easy. Now, what about elements with costs greater than epsilon opt? Let's see. If the value of the element is greater than epsilon by opt, and optimal of this opt is the sum of values of all elements I take, then I can take no more than 1 divided by epsilon of elements. So number of elements like this, so number of these big elements is no more than 1 over epsilon. Yeah. So I can, in optimal solution, there are no more than 1 over epsilon elements. Yeah. Again, opt is the sum of values of this element. If each value is greater than epsilon opt, then I have no more than 1 over epsilon elements. Now, epsilon is some constant. So 1 over epsilon is some constant. So what I can do? I can iterate for all possible sets of this number of elements. So I can try all possible subsets of elements of size at most 1 over epsilon. How many subsets should I try? I should try about n power 1 over epsilon subsets. Yeah. Now again, epsilon is a constant. So this is some polynomial, right? But the degree of this polynomial is increasing when I decrease the epsilon. For example, again, if I take epsilon equal to 1.11, so here I will have n power 100. It's not exactly what you want. Yeah. So it's still polynomial solution, but quite slow solution. So not all polynomial solution doesn't mean it is fast in practice, right? So some polynomial solutions are not usable in practice. So if you have polynomial solution like this, then for any big value of n, it is just not practical. But still, it is polynomial. That's interesting. Again, interesting thing that for any epsilon, you can build a polynomial solution. So any approximation of Knapsack problem is polynomially solvable. The degree of polynomial is bad, but it's still polynomial. And yes, number of subsets actually. It's number of ways to choose from n 1 over epsilon. But it's basically the same. So if epsilon is constant, they're just the same asymptotics. So yes, so it's number of ways to choose elements if you can duplicate the elements. We do not duplicate the elements, but asymptotics is the same. Yeah. So it's slightly less, but the asymptotics is the same. Again, whole solution. How to solve Knapsack problem for the given epsilon value. Let's split all elements into groups. One group of elements less than epsilon opt, another group of elements greater than epsilon opt. Now, for the second group, we iterate over all possible subsets. Now, for each subset, we run the greedy algorithm. So we take this subset, run the greedy algorithm, find the optimal solution for this subset. Now, when we will iterate all these subsets, we will iterate so there is some optimal solution. In the optimal solution, they have some subsets. So we'll iterate all possible subsets. So we will iterate over the subset which is in the optimal solution as well. So we take the subset which is in optimal solution, then run the greedy algorithm, and add all other elements, so the total answer will be no more than alpha minus epsilon by opt. That's almost all. But in reality, it's a little bit more complicated. What's wrong in this solution? Can you see the problem? It's almost good, but it has some small weakness. Again, what happens if you try to program this algorithm? So imagine you want to program this algorithm. So you want to split all elements into groups. One group of elements less than epsilon opt, another group of elements greater than epsilon opt. What problem will you have? The problem is this. The problem is you don't know the value of opt. So you want to split all elements into groups, but you don't know this value. Huh? No, the optimal solution has elements in both groups. That's true. That's true. But that's not a problem. We can iterate through all subsets here, and then for each subset, run the greedy algorithm. Yeah. So in optimal solution, you take elements in both these groups. But that's not a big problem. So you iterate through this subset. For each subset, run the greedy algorithm, and then take the minimum. Yeah. The problem is you don't know the value of opt. So you can't split the elements into these two groups. But we find some approximation of opt. So let's run this first approximation, find two approximation of opt. So let's try this thing. Let's call it somewhere A. So let's call this value A. And let's use this A here instead. So we'll try this, not epsilon, but epsilon A. So what we know about this A? We know A is at least opt, and it is definitely less or equal than opt. Yeah. So here I have, say, less than epsilon. So if it is less than epsilon A, then it is definitely less than epsilon opt. Since A is less than opt. Here, I know that CA is greater than epsilon opt. It means epsilon A. It means it is greater or equal than 2 epsilon. No, I have 1 over 2 epsilon opt. So in my optimal solution, there are not 1 over epsilon, but 2 over epsilon opt. Slightly worse, but still polynomial. So here, so if I want to have error at most 1%, I need to have solution of n in power 200. It's even worse, right? But still some polynomial. Okay, so this approach has built you some polynomial solution for each value of epsilon, but it's completely unpractical. So it's nice in theory, for some problems it's the only thing we can do actually. So there are some problems when you can't find any better solution than something like that. But for knapsack problem, situation is even better. So for knapsack problem, we can build a epsilon approximation for any value of epsilon without this stuff. So we can build it has some name, I don't remember. So we can build solution with time complexity. So the power of n do not depend on this epsilon. That's even more interesting. Use randomly multiple and time greater reverse approximation. How did it have so if you run it multiple times, how can it give you better approximation? Here. Okay. So you can run and make beta value of A and then run it again. Maybe it can improve something. So you just choose different epsilon here, find some better epsilon approximation. Yeah, maybe you can improve the solution like this. Yeah. So you first pick some small epsilon, find the solution, then put this solution here, decrease the epsilon, and then find another solution. Yeah, it may work. It may work. But it's again, for knapsack problem situation is even better. So let's build much more interesting algorithm for the knapsack problem. First of all, we discussed knapsack problem in the first semester when we talk about dynamic programming. So sometimes you can solve knapsack problem using dynamic programming, right? The book? I don't know. Let's talk about books later. So, what I was talking about? So sometimes you can solve knapsack problem using dynamic programming, right? So we discussed it in the first semester. To make it solvable using dynamic programming, we need our values to be small integers. Yeah? So if usually you solve knapsack problem when your weights are small integers. So you have a dynamic programming when your state of your dynamic program is a current weight of your elements. Yeah? But you can do it from the other end. So you can make the state of your dynamic program as current value of the element. And it will allow you to solve knapsack problem when you have small values. So if I have small values, small integers, fully polynomial approximation. Yeah, it's nice. It's a nice name. Nice. So if my values are small integers, I can solve knapsack problem exactly using dynamic programming. So how to use dynamic programming to solve knapsack problem? Well, basically you make a state of your dynamic programming is a current sum of the values of your elements in your knapsack. So you make like something like d x, where x is sum of your values. Yeah. And then you take the element and try to put it in your knapsack or not. So if you put the element in knapsack, you increase this x. And again, the value of d is some like minimal weight of the elements with this total value. Yeah? So this dx is the minimal weight. So minimal total weight. Minimal total weight of elements. With total value equals to x. Something like that. And then you take an element and if you put it in knapsack, you increase this x. If you don't, you just get the same x and so on. So you have this dynamic programming. In the end, it will give you the maximal value. So and then you just take the maximal value of x such that d of x is less or equal to s. So ends is maximal x such that d of x is less or equal to s. It's pretty simple dynamic program. Now, what's the problem here? Problem here in my values are not small integers. They may be not small and maybe even not integers. So what I can do? I want to build another problem with the same weights, but with small integer values. How to do it? Well, let's modify my values. Let's say that my modified value I. Let's do it like this. Yeah, like this. So let's take the value divided by epsilon, maximal value by n, like this. Yes, I will round it down, but I want to build a small integer. So I actually, let's put it here. So I want to I want to divide it by the value epsilon over n. Let's do it like this. Okay, just to make it more clear. So I want to ci divide by epsilon over n c max, like this. So this will give me small numbers, and this will give me integer numbers. Yeah? So the numbers will small integer numbers. Nice. So what's next? What's next? No, actually, okay, let me draw a picture. So these are my values. These are my values. Yeah. So what I'm doing here, I measure these values using some. So this is my unit of measure, right? So I take this. This is like the size of the block, and I'm measuring these values using these blocks. So let's call it. So this value is some blocks. So in each, here I have these some blocks here. I have 2 blocks here, 1 block here, like 3 blocks here, 2 blocks here, and 2 blocks here. So my new values will be like 2, 1, 3, 2, and 2. Something like that. And the length of this block is exactly this. So it's epsilon over n c max. Now I have small integer values. Let's solve the problem using dynamic programming. What we will have? Let's see. So, what is time complexity of my dynamic programming? My dynamic programming, I have this state x. X is no more than total cost of all elements, total value of all elements. So in my dynamic programming here, this x is no more than sum of all c. So what is the maximal value of c prime here? So c prime I. So again, I divide this ci by c max. So this value is less or equal than 1. Here I have epsilon over n, so the value of ci is no greater than n over epsilon, right? Now, when I run dynamic programming, the complexity of this dynamic programming will be, again, I have, so this sum of c prime is no more than n squared over epsilon, right? Makes sense. Looks fine. So it's n squared over epsilon. So the total time complexity of my dynamic programming will be total value of all elements multiplied by n. So time complexity of dynamic programming will be like n power 3 divided by epsilon. Using bits, I want to find. So I want to find here. I want to find some minimums. Yeah. If I've only, the problem is I have both weights and values. If I have the same weights, so if I just want to find, if I have only weights, so if I just want to, it's another just variation of the Knapsack problem. If you just want to put the elements, so the total weight of these elements is maximal possible, then you can use bit set and stuff. But here I have both values and weights, so I can't use bit sets here. Now, this is my time complexity. Now, what is the error? Again, that's the whole solution. That's the whole solution. So again, how to solve knapsack problem? You modify your values like this, and then run dynamic programming. Dynamic programming will give you some optimal answer for this modified problem. You use this modified solution as solution for your initial problem. And this solution will give you some good approximation of your optimal solution. Why is it a good approximation? Well, it will give you some set of elements with total weight no more than s. What will be the total cost of this element? Total cost of these elements will be just sum of these blocks. So what about the difference between your solution and optimal solution? Your solution may be different from the optimal solution because you have these leftovers here. So in each block you have this leftover here. So this, and this, and this, and this. So we just remove these tails because we rounded it down right here. So what is the size of this? So the size of this thing is less than epsilon over n C max. Yeah. So the optimal solution is no more than our solution plus the number of elements multiplied by this error. So for each element, give us some error to the solution. So we have at most n elements in knapsack. So it will give us at most epsilon over n C max. Now, C max is obviously less or equal than the optimal solution. Right? So I have epsilon opt here, I move it to the left, so I have n's with 1 minus epsilon opt. That's all. So that's how you build epsilon optimal solution in this time complexity. Again, this is much better. Okay, well, let's try to think about it. Let's try to think about it. Again, for example, if you make epsilon equals to like this, then here I have n cube divided by this thing. So I have 100 by n cube. So it's just 100 times slower than just your regular knapsack problem. It's not great. So you multiply your time complexity by 100, but it's much better than what we had before. Before we had n power 200, and just here we have multiplied by 100. It's much better. It's actually usable in practice. So you actually can build approximate solution for knapsack problem using this approach. Yes, and you can modify this for some variations of knapsack problem. So this is just a classical knapsack problem. If you have some variation of knapsack problem, you can improve it for your variant. That's all. Okay, that's all for today. Okay, so we discussed some different types of approximation algorithms, and so for some problems we have some simple two optimal solutions. For some problems, we have some complicated solutions, which give us some approximation. And for some problems, like for knapsack problem, we can build approximate solution for any epsilon, and it's actually pretty fast. So different problems may have different approximate solutions. It depends from problem to problem. Okay, so that's all. See you next week.